Hello, my name is Guillaume Damian. I'm going to present this work about strip Halfedge data structure for parallel computation of arrangements of segments. This is a joint work with David Corjoli and Pierre Bourca. Arrangement of segments is a famous problem used in many different applications. Given an input soup of segments, we want to compute a topologically valid arrangement, which is a partition of the plane in vertices, edges, and faces. In order to compute an arrangement of segments, we need, firstly, to efficiently compute all the intersections between all the segments. Secondly, we need to numerically represent these intersections using exact arithmetic in order to avoid floating point errors. And thirdly, we need a combinatorial data structure in order to represent the topology of the arrangement. And there are two main challenges. Firstly, we need to certify the computation both geometrically and topologically. And secondly, we need to be able to handle very large datasets. There are many related works around the computation of arrangement of segments. First, the state-of-the-art algorithm allowing to compute all the intersection between a set of segments is the sweep-line algorithm defined by Bentley and Ottman. There are only few papers that study how to compute an arrangement of segments in parallel. First, there is a work of McKinney et al., which used a strip decomposition and the sweep-line algorithm. This paper has three main problems. First, it only computes a set of segments and not a real arrangement. Secondly, it does not use exact arithmetic, and thus their method has errors or crash. And thirdly, there is no general strip position, leading also to error in the computation. There are also other methods that define parallel arrangement computation, but for some specific massively parallel model, and these algorithms are mainly theoretical. In this work, we have three main contributions. Firstly, we define the strip Halfedge data structure, which ensures a global topological consistency of the overall planar map. Secondly, we define a parallel algorithm based on this strip Halfedge data structure, which is fast. And thirdly, we define a stream algorithm, which only required a low memory footprint in order to compute the arrangement of segments. And we solve several previous limitations of related works. First, our solution used a multi-core model and our source code is available. Secondly, we represent both the topology and the geometry of the arrangement. Our method is robust. We use exact arithmetic construction and exact geometrical predicates, and we have no constraint on the location of the strips. Let us start by some preliminary notions. An Halfedge data structure called s-HDS allows to represent a planar partition. It contains a finite set of half-edges and two relations defined on these half-edges, next and opposite. Three optional relations can also be defined: prev, vertex, and faces. Next and prev allow to iterate around faces, and two other relations allow to iterate around vertices, next v and prev v. So now we can define the stripped HDS. First, we define strips, illustrated here on this example by the red lines. We use disjoint interval in order to obtain a full partition of the plane. With this definition of strips, a vertex of a planar partition belongs to exactly one strip. However, an edge belongs to one or several strips. When an edge belongs to several strips, it is called critical and drawn in blue in this example. Edge B here belongs to strip S1 and to strip S2. So this edge is critical. So now this is the definition of strip Halfedge data structure that I'm not going to detail. I'm just going to explain it on an example. Given a 2D planar partition P and S strips, the strip Halfedge data structure that encodes P is mainly a set of partial HDS H1 to HS, where each HI describes locally the restriction of the planar partition to the corresponding strip. In the strip HDS, we can see here on this example that each vertex is only represented in the partial HDS that contain it. For edges, it depends if it's a critical edge or not. A critical edge belongs indeed to several strips, and thus it is described in all the corresponding partial HDS. For example, here HB is described in H1 here by these two Halfedges, and is described here in H2 by these two Halfedges. We can see here on this example that some Halfedges are not associated with any vertex. This is, for example, the case for Halfedge 1. Indeed, its vertex does not belong to strip S1. So for this Halfedge, vertex 1 give null. This is why the HDS are partial, because some relations are not defined. These Halfedges are called external Halfedges and are drawn here on this figure in blue. Then we define local operators for each partial HDS. First, for non-external Halfedges, the definitions are exactly the same than for a classical Halfedge data structure. So we define prev v, next v, and opposite for each partial HDS. For external Halfedges, these local operators are not defined. For example, here in H1, for Halfedge 1, there is no prev v because there is no vertex in H1 at the origin of this Halfedge. The definition of the strip Halfedge data structure is almost finished. We have a set of partial HDS correctly defined, but these partial HDS are totally independent, and we need a way to link these different parts together. This link is done through a global labeling of Halfedges that describe critical edges. In this example, edge B is critical, so we give label B to Halfedge 2 in H1 and to Halfedge 10 in H2, and we give negative label for Halfedges in other orientation, so here minus B for Halfedge 1 and for Halfedge 9. Now we are going to define global topological operators for our strip HDS. First, we define for each Halfedge its non-external Halfedge, NE, having the same identifier than H. It is easy to define an algorithm here that compute NE of any Halfedge. Now, thanks to the new operator NE, we can define the global operator of a strip Halfedge data structure that allows to see a s-HDS like if it is a classical HDS. So first, the set of Halfedges of global is the union of all the non-external Halfedge of all the partial HDS. Here on this example, we are going to take only the black Halfedges. Secondly, the set of vertices of global is the union of all the vertices of all the partial HDS. And thirdly, the set of faces of global is the same than the set of faces of the s-HDS. Then, for each Halfedge of the global HDS, we can define its operators by using the local operators of each partial HDS and the NE operator. First, next v, prev v, vertex, and face are directly given by the local operators of the partial HDS. Then, opposite is obtained by combining opposite in the partial HDS and NE operator. Now we are going to use strip Halfedge data structure in order to compute arrangement of segments. First, we defined an algorithm allowing to compute an arrangement of segments in parallel. Given a set of segments as input and some strips, we first label each segment of the set with a unique identifier. Then, in parallel for each strip, we are going to compute the different partial HDS describing the arrangement of segments concerned by the given strip. Then in the second step, we need to remove vertices and Halfedges which are outside this strip. What is important here is since these different partial HDS are fully independent, this loop can be done in parallel. And the global consistency of the s-HDS is only ensured by the initial global labeling. we use a similar idea in order to define an algorithm allowing to compute an arrangement of segments read from a stream. Here, in this first loop, we read the different segments from the stream and we label the segment with a unique identifier. Active segment contains a list of segments of the current strip. Then we can compute the arrangement of this segment for the current partial s-HDS. We remove the vertices and halfedges which are outside the current strip, and now, since the different partial s-HDS are fully independent, we can swap the current partial s-HDS to disk and continue to read the next segment and compute the next partial s-HDS. The interest of this algorithm is it only requires a low memory footprint in order to compute the full arrangement of segments. Now I'm going to present our experiments. We implemented our stripped HDS data structure and the two methods of parallel and stream computation. The code is available here. We use Seagull in order to use exact arithmetic, and we compare our solution with the Seagull arrangement package. Note that our code uses the Seagull implementation of the three-plane algorithm. In our experiments, we use three different data sets. First, some random generated data. Here, the best case for our stripped version where there is no critical edge, and the worst case for our version where each segment is critical. Here, this is a sketch from the OpenSketch repository, and we also use 10 different countries from a GIS dataset. In this first experiment, we compared the computation time of the arrangement of segments for the Seagull method and for our method for different number of strips. And here we fix the number of threads equal to the number of strips. We can see that the computation time decreased when the number of threads increased. And note that the speedup is not perfect. This is due to the number of critical edges that increases when the number of strips increases. This experiment is the same, but now for the GIS dataset. We can see here the different computation times of the arrangement of segments for Seagull and for our method. In average, our method is 3.5 times faster than Seagull with 32 strips. We evaluated the overhead due to the critical edges that belong to several strips. First, for memory space, for one strip we use 2.46 GB of memory, and for 32 strips we use 2.96 GB. Secondly, when we traverse the strip Halfedge data structure, we need to jump over external Halfedges, and for one strip the complete traversal takes 0.52 seconds, and for 32 strips it takes 0.57 seconds, so the overhead is very small. For this last experiment, we compared the memory space required to compute the arrangement of segments by using Seagull, our method with one strip, and our method by using the stream arrangement computation. For that, we use the HipTrack tool, and here this is one result for the Australia GIS dataset. So for Seagull, we required at the end 2.3 GB of memory. Our method with one strip required at the end 1.5 GB of memory. And obviously, when we use the stream algorithm, we only need 15 MB of memory, which is very interesting in order to compute an arrangement of segments for a huge dataset. So now, to conclude, in this work, we define the strip Halfedge data structure. We prove some links between HDS and strip HDS, and we define two different algorithms to compute arrangement of segments, one parallel and one streamed. As future work, we want first to define topological operators allowing to directly modify a streamed HDS, for example, edge contraction. We want also to define operations allowing to merge or to split different strips, and we would like to extend this work in 3D in order to compute arrangement of planes. Thank you for your attention, and if you have any questions.